In this video, we are going to continue our discussion on uniform flow. So in the previous video, we had looked at what is called the Chezy's equation, which relates the velocity of flow in uniformly flowing open channels to the hydraulic radius and the bed slope. Now note here that although the original empirical formula proposed by Chezy was for uniform flows, the Chezy's formula is actually applicable both for uniform as well as non-uniform flows. So in order to apply this for non-uniform flow, we need to replace the S with SF. So we write V equal to C times square root of R times SF for non-uniform flows. And I was mentioning in the previous video that although Chezy's equation was originally proposed entirely as an empirical equation, later on its links with fluid mechanics and particularly boundary layer theory were established. So, and this is how sort of hydraulic engineering gives you a flavor of the synergies between theoretical knowledge and what exists in reality in nature. So let's look at some more numbers here. So when you have fully rough flows, that is the shear velocity times the roughness height, Ks is the roughness height, divided by the kinematic viscosity. When it is larger than 100, then the flow behaves to be fully rough, and we see again an empirical relationship that relates friction factor with the roughness height. And here, as expected, when you have fully rough flows, the friction factor is independent of Reynolds number. So it depends on the hydraulic radius and the roughness height. What is more interesting, another interesting fact to note here is the fact that this is a logarithmic relation, and this comes from those logarithmic velocity distributions. So if we look at some values of Ks for real channel surfaces, if we have smooth cement plastered surfaces, then the value is as low as 0.001, and if you have rubble masonry as your channel bed material, then the roughness height is 0.02, and these are both in feet. So we see here that even if we make a large error in estimating Ks, we would end up in only small errors in the value of the Chezy's coefficient because of this logarithmic relationship. Therefore, in reality, estimation of Ks is very difficult. However, for civil engineers, for practical purposes, it doesn't really matter, because even if we make large errors in estimating Ks, the errors in the Chezy's roughness coefficient will not be very large. Now let us look at this problem from a dimensional analysis perspective. And this is a homework for you. So we have tau naught, the shear stress, is a function, and this we know from physics. Know from experience. And physics. So the boundary frictional resistance, shear stress tau naught, is a function of the density of the fluid, the viscosity of the fluid, the acceleration due to gravity, the velocity of the fluid, the hydraulic radius, the roughness height, and C, N, and U. These are all non-dimensional. These are non-dimensional terms, these three. C represents a factor for the cross-sectional shape. N represents the degree of non-uniformity of flow, and U represents degree of unsteadiness. So this relationship between tau naught and all these parameters are generic in nature. It applies to non-uniform and non-steady, unsteady flows also. And we are going to derive, and this is a homework for you. So you are going to derive using Buckingham's pi theorem the relevant non-dimensional quantities. And when you use Buckingham's pi theorem, eventually you will end up with this relationship where tau naught by rho v square is a function of the non-dimensional terms, and when you work this out, you would find out that Reynolds number is a non-dimensional term. What's this term here? This is nothing but relative roughness for open channels. Again, the Reynolds number you will get in terms of the hydraulic radius. So this is your relative roughness, and this is Froude number, and these three are already non-dimensional terms. So what we essentially see here is tau 0 by rho v square can be related to the frictional factor. It's nothing but a constant times the friction factor. So the friction factor is a function of Reynolds number and relative roughness, which is exactly what we had seen for pi flow, except that here your Froude number and other parameters are also important. So this is what we get from dimensional analysis, and this quite amazingly is similar to what we had obtained in pi flow. That is, the friction factor depends both on Reynolds number and relative roughness, and experiments, observations in real life open channels show that when you have Reynolds number very high, for large Reynolds number, friction, and which is what we see in reality in most open channels, friction factor is independent of Reynolds number. In the next class, we will look at further extensions of Chassis equations and other resistance laws, one of the most important ones in hydraulic engineering, which is called the Manning's equation. So see you.